Hello everyone, welcome back to alkaline hydroxide 784, and today we are looking at part 2 of the vaccine series, I guess. And this is about the ingredients that I saw in the vaccine, as in not the actual vaccine but in the booklet that they gave, as well as the history of the vaccine and how it came to be. So as you can see, when I actually went to get the first dose, I got this booklet, and inside the booklet it actually told all the information of the vaccine. So one of the things that was actually written in the booklet was the ingredients of the Pfizer vaccine. Of course, you can find this online, and today I'll be just focusing on this bunch of ingredients and not really look at the other ones because I think they have similar ingredients, it's just like some slight variations in terms of how they're done. So as you can see, some of the ingredients sound like, just gibberish, but in a way I can help you figure out what they are, and if you understand chemistry, how the name refers to the actual chemical. Yeah, so let's go. So once again, I'm just gonna remind you about how this whole thing is. It's like three parts. So this is the second part, and we're gonna look at the chemistry today. So the first and the most important ingredient, of course, is the thing that the vaccine is supposed to deliver. And the thing is that they write this ingredient as BNT162B2 mRNA. And you might think, oh, okay, it's the mRNA, it's the messenger RNA. And yeah, that's what I think too. But apparently, it's not just the RNA, but the entire lipid nanoparticle kind of. Actually, no, it's not really the lipid nanoparticle because the other ingredients help to create the nanoparticle. So this is actually just the RNA. So if you want to see this particular manuscript, a manuscript is basically, it is going to eventually be something that you can just cite and refer to when you're doing research, but at the moment it hasn't been fully peer reviewed. So because it was only released like 2 days ago or something, and yeah, that's why I'm not gonna look through the actual manuscript, the whole thing, but instead look at the description that they provided here. And I'm gonna explain some of these terms that have been highlighted. So as you can see, this orange ball is what I'm gonna represent the lipid nanoparticle with. So if you open up the ball, you will see inside that there is some RNA, and I'll explain to you what this is. So first off, the lipid nanoparticle is like a spherical, okay, I don't know how spherical it really is, but it looks like somewhat like a cell, but it's not a real cell, it's just the membrane. So the membrane is made of a monolayer of lipids, and lipids are basically fat molecules, but they come in all different kinds of lengths and sizes. So yeah, they're lipids, and since it's nano, it is 10 to the power of -9 meters, and that is really tiny, but there's even tinier measurements. So yeah, it's a somewhat recognizable size in terms of biology. And the purpose of this lipid layer is to prevent the RNA from getting destroyed before it does what it needs to do, aka get to the cell. And yeah, the phrase here that you see is this nucleoside modified messenger RNA. So why did they mention nucleoside modified? Well, the original RNA is made with nucleotides, but what they've done here is use nucleotides that do not have the phosphate group, and they use that to make the RNA instead of the nucleotides. And this is to prevent the cell from destroying the RNA or from destroying itself when the RNA gets in. And we need the RNA to successfully get into the cell in order for the cell to make the spike protein and then get an immune response to it. Yeah, so we don't want anything getting destroyed in the process. And messenger RNA, I think we all know what that is. It is like the one-stranded counterpart to DNA. Of course, it's not the exact same as DNA because it's made with ribose and not deoxyribose. And also, it's it has uracil instead of tyrosine. Wait, I don't remember the name, but you know what I mean. U instead of T. Uh, and yeah, of course, the spike glycoprotein. So this RNA codes for the glycoprotein, which is what we saw last time. And this glycoprotein is going to be made in the free fusion conformation, aka the shape that is in before it binds with the receptors. Yeah, that's what it's going to make once the RNA gets into the nucleus of the cell. So the first ingredient on that list is something called 4-hydroxybutyl acene diol, bis hexane 6,1 diol, bis 2-hexaldecanoate. Oh gosh. It is hard to say the whole thing, but it's still better than some other things that are even harder to say in, not necessarily in this ingredient list, but in other places. But okay. I try to, think of the structural formula, but staring at this, even if I have studied H2 chemistry, my ability to do this isn't that great. So let me just show you the actual version that you can find online by just searching the name, and you should probably do that if you can, because we have Google, might as well use it. And in the actual ingredient list, they missed out the first, the bracket, the very first character in this whole thing. They missed out the bracket, the half of the bracket, which is quite funny. But anyway, that's not the point. So you might be wondering what this even means. What is this 4-hydroxybutyl blah 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 decanoate? Well, you can see the structural formula, but some of you may still not understand what this is. And as written here, it is a lipid with a nitrogen. That's a very crude way to describe it. So 4-hydroxybutyl is the thing that's in the box right now. Butyl is butane with 4-hydroxybutyl, so the hydroxyl group is at the end of the butane. And the butane is not just butane, but instead attached to the nitrogen, so it's 4-hydroxybutyl. And we have the nitrogen, which is the reason why this thing is called acene diol. That's the general structure, like a nitrogen with 3 hydro, like ammonia kind of a vibe. But since there's other things instead of H, it's not ammonia. Yeah. And then we have the bis hexane 6,1 diol, and that is what this is. Yeah, so that is the hexane, the carbon chain of 6 carbons. And you might be wondering what is the 6,1 diol thingy. Well, it is attached at 6, and the 1 just means they're both attached to this particular, the next molecule, that next part of it that I'll be showing you, the first position in that. So the 2-hexaldecanoate is basically what you see here. It's like a ester, I guess, ester between a hexane and a decanoate. Wait, no, it's like, you know what I mean, like the parts are made of 6 carbons and 10 carbons respectively. It's an ester that comes from an alcohol and an acid. So that's the whole thing. Pretty much the whole thing. So the second one is something that's a little bit easier to understand, and it is 2-polyethylene glycol 2000 and diacetoamide. I hope I spelled it correctly here. I hope. So polyethylene glycol, or PEG, is a surfactant. So it can polymerize. You can make polymers or some sort of plasticky thing with it, and that's why you have a N here. So the first box here is not referring to a polyethylene, but instead to the to the middle part of this thing, which is the acetamide in the sense. And yeah, that's the general structure of it. No, that's actually, yeah, that's the general structure. And then this part is the PEG, polyethylene glycol, And the 2000 just means that it is 2000 Daltons in size. So that's like it's referring to like the molecular, like the weight of the thing. And you use the unit of Daltons to refer to organic molecules. So yeah, that's what we have here. It doesn't mean that there's 2000 polyethylene glycols, but more 2000 is the weight, the overall weight of the entire like chain of polyethylene glycol, which could be more of like 35 to 40 around there. I didn't calculate that, so that's how long the chain is. And then we have these two things which are actually you know 10 carbons, and that's the reason why there's a decal word, not really word, like a prefix in there, because there's 10 carbons and that's attached to the end. So instead of using numbers, they use the end. So that's why instead of putting 1 diethyldecyl acetamide, they put N, because you don't really have a number to refer to the N. Yeah. So this is basically just a PEG attached to some carbon chain to make it like a lipid, basically. And the final, actually not the final one, the third one is a phospholipid, and it's called 1,2-disteroyl SN glycerol 3-phosphocholine. And this is a phospholipid, and in fact you can probably if you look at it closely enough, you can recognize the typical glycerol kind of lipid. And here we have the glycerol. You can see that there is, I mean, it doesn't look like the nice neat diagram of a straight glycerol, but you can see that there's 3 carbons. Maybe let me use the mouse. There is 1, 2, 3. Yeah, so there's 3 carbons, and there's oxygens on all of them, and you can kind of tell that there's a glycerol here. And attached to the glycerol is these two things, which are this diasteroyl thingy, and that's the reason why it's on 1 and 2. It's on the first and the second carbon. The diasteroyl are there. And the SN just refers to the fact that there's this stereo kind of arrangement to it. Like the stereoisomers, they have different arrangements. So this is a potential stereoisomer. And you can tell there's like a wedge here. That's why they use the SN. It has nothing else much to do with the whole thing. And of course, we have this thing called phosphocholine, which is like this phosphorus with a bunch of, it's like a phosphate group with a random carbon chain and a nitrogen attached to it. There's phosphocholine, and it's on the 3rd carbon of the glycerol. Yeah, so this is a phospholipid because there is a phosphate group kind of thing here. Not really a phosphate group directly, but phosphocholine. Yeah, that was the 3rd one. And the 4th one is cholesterol. So cholesterol is something we all actually are familiar with. It sounds more familiar than literally the first 3 things I mentioned just now, and something you probably will not be scared of unless you eat too much of it. But what is the purpose of cholesterol? Well, cholesterol is actually quite important in terms of our cell membranes, because it allows the cell membrane to be a little bit more fluid. So if you have a lot of cholesterol in the cell membrane, it will be very fluid, but also quite soft, so it's easier to destroy the membrane. Whereas if you don't have a lot of cholesterol in the membrane, it is quite stiff, so the cell cannot really, it's a bit harder for it to move around and do things like that. Yeah, that's the idea of cholesterol. And it is used here because we are creating a lipid membrane. So how do these lipids help the vaccine? As I mentioned, we have something called lipid nanoparticles. And that's like the thing that I represent in orange. And these things will all form the lipid membrane. So I'm not going to ask you what this is, because saying the name will probably take like 2 minutes. But this particular thing, which was the very first one, I don't even remember the name, but this one is the, what do I say? It's a cationic lipid, so it's used to attract the RNA and keep it in place inside the liposome. So we'll call these lipid nanoparticles as liposomes. You can do that too. And that's what help it to stay inside the liposome in a sense. So that's good. You put that in. And of course the PEG, the pegylated lipid. So what does that do? Well, PEG is a surfactant. So it's kind of like your soap particles, like the stuff in your soap, which helps to keep water and oils together. So this will help it to stay as a lipid nanoparticle and also stay inside that water, like an emulsion kind of thing, to stay suspended in the water, because at the end of the day, you're just going to add water to dilute it to the maximum volume that they have, and to also make it easier to actually inject it into someone. So yeah, this is the surfactant. There you go. And we have these two, which also help with keeping the lipid layer, somewhat present. Like it gives them some structure, and they form quite a bit of the lipids in there as well. So as I mentioned, cholesterol helps to keep it a little bit flexible so that it doesn't just, isn't too stiff in terms of the membrane. And also the what was the other one, the glycerol one, that one also helps with keeping the membrane intact in a way and give it some structure. And yeah, that were the first few ingredients. So after that, you see 4 other ingredients, which are all salts. So I'll just tell them all at one go. They're actually quite normal sounding salts. They're like sodium chloride, which is table salt. There's potassium chloride, which could be an alternative to table salt if you need to reduce your sodium. Yeah, in fact, there are people who use potassium chloride. Then there's sodium phosphate and potassium phosphate, which is basically, instead of chloride, you have a phosphate group. And in the body, sodium, potassium, and chloride are all very important in the the electrical signaling kind of stuff. And phosphate is also very important, as it's there in like literally all our DNA and also in ATP and so many other molecules. So these things are quite useful for the body actually. And it also helps the inside of the liposome and the outside, everything to be like the same tonicity as the blood, so that it doesn't create any problems or accidentally cause some sort of liposome swelling or something. It's a bit like how you have those images of a red blood cell in an isotonic, hypertonic, and hypotonic solution. So only the red blood cell in the isotonic solution is good. The other two, one of them will swell up and one of them will shrink. So we just need to make sure that the tonicity is around the same. Yeah, that's the point of the salt. And of course, we have the last ingredient written in that list, which is sucrose. And as we kind of know, it is something that is sweet. And it is actually used in many pharmaceutical drugs because it's like a filler. It's not harmful or anything, it's just a filler. It's like you easily use it to bind things together or to fill up the rest of the volume. Because in tablets especially, the actual API, the active pharmaceutical ingredient, is quite small in concentration. So if you were to literally only compact that, you may end up breaking it apart before you could even use it or something. So sucrose helps to keep it in place and help it get into the person when they take the tablet and not accidentally just break up, and spill on the floor or something. But in this case, it's not a tablet, it's a solution of sorts or emulsion of sorts. It just helps to keep things together, give a little bit more viscosity to the solution. And by giving viscosity, it also helps the emulsions remain as an emulsion, because I've learned that if sometimes stuff inside the an emulsion can settle out either to the bottom or to the top, depending on the density. So in the vaccine, you kind of want it to be around the same concentration everywhere. And even if you can shake it a bit to help that happen, it also helps to prevent it from settling out too much to begin with. Yeah, so sucrose helps with that. And in a way, it also helps to prevent bacterial growth, although I'm not sure how much they use, whether they use enough to do that. But if you put enough, then it could prevent bacterial growth. And yeah, so it is topped up with water, and that's basically the vaccine. And if you've been following through, you can tell that there's nothing much to be scared of. Like even PEG is quite a common thing. I've heard of it many times, and it is biodegradable, so no worries. It's not going to really harm you in any way. It may irritate you a bit, but it won't harm you. So none of the ingredients will actually cause any trouble, and of course there's no microchips or anything like that in there. I mean, even if they were to attempt to secretly put in a microchip, it wouldn't make sense because it wouldn't function, like wouldn't have enough functionality to do anything, and it'll be quite hard to put it into a solution that more. As I just mentioned, things the solution stuff can actually settle out, like the emulsion stuff can settle out. I keep using solution and emulsion interchangeably, but they're not exactly the same thing. But you get the point. Like I don't see the point in doing that. And even if you did somehow get a microchip inside there, it'll be quite hard to get it into the needle. So what's the point? There's absolutely no way that people would be putting microchips into a vaccine. And even if they did, it probably won't get into a syringe. There you go. But yeah, there's nothing dangerous inside this. Wait, so now that you've heard about all of the ingredients, and you'll be like wondering, wait, how did all of this even become a thing? Like, how did they come up with the idea of doing mRNA vaccine instead of a traditional vaccine where you just put a inactivated or a dead virus? So this is not a new concept actually. mRNA has been a concept that came up in 1990 by someone called Kathleen Carrico. And she is, she's quite, I think we definitely have to thank her for being able to think of this idea so long ago. But unfortunately for her, back then in 1990, she couldn't get any grant, like her grant wasn't approved, so she couldn't really do any research within the university that she was at. So eventually she met Drew Weissman in 1997, and the both of them eventually did some stuff, like did some research on it on their own without much help from the university itself. And eventually they started their own company and continued to research on this. And once they got some success in the last decade or so, Kathleen has joined BioNTech, so she's actually working in BioNTech, and that's how BioNTech managed to get the vaccine out because they have her expertise, and basically you're in good hands. Okay, this vaccine was in good hands. She's the literal inventor of, I don't know whether you can say inventor, but like the person who came up with this concept to begin with. And the other thing that she managed to do was to figure out how to make sure that mRNA doesn't get destroyed too quickly, which is the nucleoside modification kind of technique. And that is what helped this whole thing become a thing. So people who might have been thinking, how did they come up with the vaccine so quickly and do everything so quickly? Well, in reality, it is not so quickly actually. It's a thing that came up as an idea almost like 30 years ago, and now only it has it managed to show its true potential as a technology that's been used. And in terms of the trials and whether it's safe, this is more likely to be safe compared to a normal vaccine, because this is not the actual virus. So if let's say you make a normal vaccine and somehow the virus is not dead enough for it to, you somehow is accidentally still alive, then it could infect a person with the disease. Whereas this is not the actual virus, so even if it doesn't work or something, like even if, let's say, for some reason it doesn't work or it just gets destroyed, nothing's gonna happen to the person. And even if it doesn't do what it's supposed to do, it's not gonna be harmful. It's just a piece of RNA. And yeah, it's not even the protein, it's the RNA, it's just instructions. And it cannot replicate itself, it cannot do anything. So it's pretty safe compared to an actual virus. And yeah, that's pretty cool, right? So in fact, this technology could be used to treat many more diseases or even create many more vaccines in the future, or even for other diseases that do not use a vaccine, but stuff like cancer and things like that. So actually, the first time I read about lipid nanoparticles, I didn't think about this particular way that it could be used, but I did know that there was some use, like investigation in using it to treat cancer. So yeah, that's pretty much how we managed to get an mRNA vaccine so fast, because it was just the perfect timing for it to, launch itself as a technology. And at the same time, the trials and everything, of course, there was instead of doing them one by one in order, they did them all at the same time, and that doesn't really remove the accuracy of the trials or anything. It still just makes the whole process a bit faster, and that may actually be implemented in the future to reduce the overall time it takes to release something into the market. Yeah, so we've actually learned quite a bit from this whole process of getting the vaccine. And yeah, before we end, I found this. Apparently, I was like, I was just looking at all the links and trying to find the structural formula for all those molecules. And I saw there's this assessment report from the European Medicines Agency, which was basically the report that allowed the use of the vaccine. I'll put the link if you want to see it. Maybe if you want, I can look through it another time, because I know this will be quite a bit of time and I don't want to spend even more time in this video. So if you're interested, I can probably do it, or if I feel like doing it, then I'll probably do it. And this is kind of more related to the pharmaceutical industry and what kind of terminologies or what kind of testing that you do with regards to a certain drug or API in a sense, in order to approve it for the market. Yeah, or for public use for that matter. So yeah, I hope you found this video useful and informative, and I hope you will feel a bit more enlightened about the vaccine. And if you're interested in getting more information, please do refer to the links, because I don't have time to go into detail into everything. So do refer to the links, or if you want to search it up yourself, you can. Please do it, because knowledge is power. So if you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye.